Good morning, students. I am R.K. Ranjan, PhD Chemistry. Hereby start our new lesson. This is a solution. This is Unit 2, and the objective of this very lesson that is well mentioned over here. You can easily understand it. Here you see is all about the description of the formation of different type of solution, expression concentration of solution in different units, and it also explains the Henry law and Raoult's law. This both are very important. Distinguish between ideal and non-ideal solution, explain deviation of real solution from Raoult's law, and colligative properties, which are also very important, and abnormal colligative properties. So these are the important points which you are going to learn in this very lesson. So just we see one by one what are the important aspect of this very lesson. You know, types of solution. Generally we find that two type of solutions are generally obvious in our day-to-day life. One is the homogeneous mixture, and another is obviously a heterogeneous mixture. So in that very homogeneous mixture, what happens here, the solutions are homogeneous mixture of two or more than two components, where each components has been mixed very nicely, and this is also called the binary solution, because two types of solutions are mixed, either in their liquid form or in gaseous form or in solid form. So we will see here lots of different type of solution. That's a very important aspect. You see here that table 2.1 is showing the types of solution. Here to the left hand side you can see over here types of solution. Here is a solute, solvent. You know that generally solute dissolve into the solvent. Solvent is always having the bigger volume. So first is the gaseous solution. Solute is the gas, liquid and solid. You just see that what type of solutions are made. When the gas mixes with the gas, mixture of oxygen and nitrogen gases are there. Liquid mixes with the gas, chloroform mixes with the nitrogen gas. Okay, where the solid and gases are mixed is camphor in the nitrogen is one of the example. And here the liquid solution, when the gas and a liquid solution, when the gas and a liquids are mixed, that oxygen dissolves in the water. You must have been remembering that while opening the bottle of Coca-Cola or a Campa-Cola, you might have seen that a carbon dioxide bubbles are coming out from the solution. This is also one of the best example of the liquid solution, where gas is mixed with the liquid. Another is the liquid and liquid, that's the ethanol dissolved in the water, is the best example. And a solid liquid solution, that's a solid is a glucose that we well understand, that चीनी वगैरह को आप देखते हैं पानी में मिलाते हैं. तो solid and liquid जो है glucose dissolved in water. Here is the solid solution, gas dissolved in the solid, solution of the hydrogen in palladium, liquid dissolved in the solid, amalgam of mercury with the sodium, and solid mixed with the solid, that's the copper dissolved into gold. Okay, students, so we are going ahead. Now it's a time to learn about this very aspect, expressing concentration of solution. You must have seen that there are so many units on the bottles of different type of solutions are written, but this type of problem also always arises in the mind, that why these things, why units are written in such a manner, and if it is written in such a manner, then what does it signify? So first of all I want to discuss with you that one is the mass percentage, W by W. Mass percentage of a component of solution is defined as a mass percentage of component. You can easily see over here the mass of the component in the solution divided by total mass of solution multiplied by 100. So here the mass percentage whatsoever is obtained in this very aspect, that will be denoted with the with the kind of tag that W by W that you have seen, and it is generally denoted when commercial bleaching solution or hypochlorites in water type of sodium hypochlorites in water type of solutions are measured. Okay, so just we see another aspect, that is the volume percentage, volume by volume. Okay students, so what does it shows? It is you can easily see it over on the bottles of the solution, which consists that ethylene glycol or other type of solutions where both solute and solvents are the liquid. Here you can see that the volume of the component is the volume of the component divided by the total volume of solution multiplied by 100. Here the components which you get is simply shown with this tag, that volume by volume. Okay, here is the mass by volume percentage. What happens over here, that the solute is taken into solute is taken by the weight, which is in the gram kg, or solvent is taken into the volume. Such type of you must have seen that kind of pediatric solutions are sold in the market, like paracetamol solutions, which is used for bringing down fever in the kids or in the adult persons. If there is a liquid solution, then it must be in the weight by volume. And one is a very significant aspect, there is a part per million. It is basically measured when the pollutants or the chemicals or small quantities are found in the traces. That means this quantity is very less. It is convenient to express concentration in part per million. You can say part per million is equal to number of parts of component divided by total number of parts of component of a solution multiplied by 6, multiplied by 10 to the power 6. Here the 10 to the power 6 is required because after multiplying with 10 to the power 6 multiplication, what happens, the amount of that traces becomes countable. It becomes its number gets higher. So it is this is the reason for that it is multiplied with this very unit, part per million, that you have also studied in the class 11th. Here is the mole fraction, that is very important. What happens, the mole fraction of the component is equal to number of moles of the component divided by total number of moles of all components, that is the mole fraction. And here you can easily see that in binary mixture means if it has two mixtures, then if a number of moles of A and B, where Na and B are respectively the solutions is A and B, and the number of moles of their components are Na and Nb. So if we really want to know about the mole fraction of component Na, then Na will be at the top and Na plus Nb is here. And if solution contain I number of components, means if it has lots of components, then we can use this very formula. Here x1 is the mole fraction, x denotes here mole fraction. So students, I think that I have already cleared this very thing. You just solve this very example which is already given over here, and it also find out the mole fraction. You can see it see in this very example 2.1. Calculate the mole fraction of ethylene glycol C2H6O2 in solution containing 20% of C2H6O2 by mass. What happens over here? You can see that molar mass. First we will find out the molar mass of ethylene glycol. Here is the 62, 4 moles of 60, and total solution is 62 grams because molar mass, and 20 gram, 20% of ethylene glycol in the whole solution. So 20 gram by 62 gram mole per gram per mole is 0.322 moles of ethylene glycol is present over there, and moles of water 80 gram. Okay, because 20% is the ethylene glycol, so rest of is the water. So 80 gram divided by 18 moles of water will find out 4.4 moles. For ethylene glycol mole fraction of silicon, moles of C2H6O2, moles of C2H6O2 plus H2O. What happens over here? 0.068 is the mole. Similarly, water, what happens over here? You just 4.444 divided by 0.322 plus 4.444, and the overall fraction comes with the 9.32. And here the mole fraction of water can also be calculated, 1 minus 0.68. So what happens, if there is a mole fraction like of two components like x1 plus x2, and which is equal to 1, because after all the whole fractions, after adding the whole fraction of a one component become equal to 1. So if we know if there is x1, xa and xb equal to 1, and if you know the x value of xb, xa can be easily calculated. So by following the same principle, this thing has been calculated. So thank you all for listening patiently. Thank you.